Now, this time with integration, we use integration by parts, but there's a little bit of a technique we need to look at here to play around with this one. And sometimes this will happen with some questions. So we want to integrate the square root of 1 plus x squared. So I'm going to take the 1 times the square root of 1 plus x squared, because, again, I haven't got a rule to integrate that one because it's not a linear function in there. So and I can't do a substitution that's going to work out nicely. So if I do the 1, integrate the 1, gives me x, square root of 1 minus x squared. Well, that's not a problem. But if I integrate the first and then derive the second, now I get a half times the 2x over this 1 plus x squared power over half. So there's the derivative of that function, which is giving me then the integral of x squared on 1 plus x squared. Now, to manipulate this, again, that one's going to be really hard to try and integrate. But if I do this and go x squared plus 1 minus 1, which you look at that can be written as the square 1 plus x squared on 1 plus x squared all to the power of a half, plus 1 on the square root of 1 plus x squared. Now notice I've got square root of 1 plus x squared there, which is what we started with, but also integral of 1 over square root of 1 plus x squared, which is, we can manipulate that one. So what I'm going to do, because it's always equal to the square root, integral of square root of 1 plus x squared, I'm going to take that one across. So notice that becomes 2 lots of the integral of the square root of 1 plus x squared dx. Now we're able to do that because this is always equal. This is always equal to the left hand side is always equal to the right hand side. So I can say 2 lots of the left hand side must be equal to this. Now the integral of 1 over the square root of 1 plus x squared is natural log of square root of 1 x plus square root of 1 plus x squared using our table of standard integrals. And then, because I've got 2 lots of that, I can just divide everything by half. So there's our integral there. Now, I've basically used the function itself and then added it in there. So there's a technique we can use sometimes and we need to use sometimes to solve some of these integrals, because they just don't solve straight out. You end up getting them recurring back in themselves, so you can start to take them over. So there's a bit of what we call recursion happening there. Have a look at this one. Don't be too scared, because it looks ugly, but it only looks a bit ugly because I'm keeping this the same all the way down the left hand side to help manipulate it. So e to the x times the sine squared of x. So I'm going to integrate the first, which that makes life easier, and leave the second. So I get the e to the x sine squared x all the way down, and that's minus integral of e to the x 2 sine x cos x, which again I'm going to have to do integration by parts here. So integrate the first, I've taken the 2 out, so integrate the first, leave the second, and then integrate the first and derive cos x sin x, which comes out to cos squared x minus sin squared x. Too bad it's not cos squared x plus sin squared x, because that would be 1. Beautiful. Doesn't work that way. So again, we're just manipulating. We're keeping this function the same all the way down, but getting 1 minus 2 sin squared x, as we know that's a manipulation we can do, because integral of e to the x dx, which makes life easier. But then we've got 2 e to the x sine squared x, which, wait on, that's exactly what we started with. So you see it's recurring back on itself. Expand that bracket out, the 2 multiplies there, the 2 multiplies there, and we get 4. Now we take that part and add it to the left hand side. So add this on both sides, gives us 5 lots of this expression. And we saw the e to the x integrates to e to the x there, which that worked out nicely for that part. But then once we've got the integral there, we've got it to equal to that expression. We divide by 5 on each of them, and gives us 1/5, 2/5, and 2/5 there, plus our constant. So there's a little trick you need to be able to do, be able to manipulate it and get it across there. This one's a definite integral this time, so you can use definite integrals. So integration by parts for x inverse tan of x. So we integrate the first, leave the second, and we just put between 0 and 1 there. We don't expand it. We won't calculate it yet until we've got all of it. But then we minus half of 0 to 1. We integrated the first and left the second. I derived the second. So we get the x squared on 1 plus x squared, which we can rewrite as 1 minus 1 on 1 plus x squared, which comes down to x on inverse tan of x, minus inverse tan of x, between 0 and 1. So that was, once we were able to get into that expression and able to write it in that form, was able to integrate. We do our substitution, and we can get down to our values there once we do our substitutions correctly. This time with from 1 to e of natural log of x on the square root of x. So I've used, because I can't integrate natural log of x, I've used x to the power of minus a half as the function. So x to the power of minus a half, integrating that gives us the 2x to the power of a half, or 2 square root of x. Natural log of x between 1 and e, left the second. Integrate the first, so there's our 2x to the power of a half times the derivative of the second, which is 1 on x, which starts to give us 2 on x to the power of a half, which we can integrate. Add 1 to the power, well, that's minus a half, add 1 to the power, divide by the power, and put our values of 1 and e in, and we're able to get our expression down to there. So there's examples using integration by parts to do definite integrals. You just keep that one all the way through. You could calculate it as soon as you like. It's not really a problem, as long as you just keep those values ready to go and being able to put the values in at the end. So keep this rule in mind. Try not to be too scared off about harder ones, and they can get hard. As you saw, there's a few hard questions in those videos on integration by parts, but be able to manipulate the functions and be careful of all the algebra and the signs to make sure you're doing it carefully and being able to get to the correct answer, and that manipulation works out okay in the end.